Okay, so today I'm going to talk about unitary groups, and in particular I will also discuss what the Cartan-Killing metric is. Okay, so let's go. So the contents of this talk are based on the unitary matrix. A typical example are the Pauli spin matrices for SU2. I will be discussing the SU2 algebra and its relation to quaternions. Then we will see why SU2 can be seen as a double cover of SO3. SO3 are the orthogonal group, in 3 dimensions. Then we will be discussing the Lorentz Group as a complexification of SU2. We will be talking about unitary matrices in n by n matrices. In particular, the well-known to the experts. When people say it's well-known, they should always say it's well-known to the expert, right? the SU3 matrices, in the formulation of quantum chromodynamics. Then we'll focus on what do we mean by a Cartan-Killing matrix that will allow us to take inner products in these vector spaces, because after all, the Lie algebra, as I mentioned, is really nothing but a linear vector space. And I'll give just a very, very passing reminder of what we call Racine and Lorentz operators for SU2. Remember when we studied quantum mechanics, there was something called the angular momentum operators that allow us to raise and lower the quantum number of the states. Remember the ladder operators, the M quantum number there, which is called the azimuthal quantum number. Does it ring a bell? Anyway, we'll go into this. Yeah. Okay, unitary matrix is essentially an n by n matrix that is Hermitian. Hermitian from the point of view that when you take the Hermitian of that matrix, it coincides with the inverse of that matrix. So essentially, it is the complex extension or the complex analog of an orthogonal matrix. Remember that an orthogonal matrix, if you remember, was essentially anti-symmetric. So the Hermitian adjoint of a matrix is defined by you take the transpose, meaning that you reverse columns, you exchange columns for rows and rows for columns, and then you take the complex conjugate. So the Hermitian of a matrix is given by this expression, complex conjugate of the transpose operation. So essentially it's a transpose followed by a complex conjugation, or you can take complex conjugation followed by the transpose. It doesn't matter in which order you perform the operation. For example, the unitary group in 2 complex dimensions is the group that preserves the standard inner product on C2. It's the complex space in 2 dimensions. So for example, if I give you two complex vectors with 2 components, the inner product is defined by this. And this inner product happens to be invariant under unitary transformations. So when you perform a unitary transformation, remember this is the 2 components of this vector. For example, this could be the 2 components of another vector. So when you take the inner product and you perform this rotation in this complex space, the inner product remains invariant. What did I have here? Yeah.
W1 star V1.
Yeah. Yeah. These are the primes. These are the transform components. So the inner product of the transform components have to remain invariant.
I guess he's saying that the Z should be V.
Ah, yeah, yes. Yeah, you are right, because here I have V, you should have B. One has to be rigorous, you're right. Okay, so the inner...
Here on the formula, before, yes, V.
V.
After you redefine Z, so it's
Yeah, but you get the idea. Essentially, you have two vectors, you perform a unitary transformation, and you want to make sure that the inner product remains invariant, okay? So this is essentially what you mean by unitary group in complex dimension, which is essentially like the complex version of what happens with rotations involving real vectors in a real vector space. Okay, so you probably all remember what the Powerless spin matrices were. You see the SU2 algebra associated with the SU2 group has three generators. Because remember, you take 2, you square 2 and you get 4. But when you impose that the determinant of your group element is 1, you kill 1 degree of freedom, so you end up with 3 degrees of freedom. So in reality, you have 3 generators. And you can choose any basis you want, but the simplest thing is to choose, for example, in this case, the Hermitian and traceless matrix. You'll see in a minute, in a second, why the traceless conditions is so important. So here you have your first generator, and you see it's Hermitian because 1 over here is the complex conjugate of 1. You know, when you look at the main diagonal, they're kind of less symmetric with respect to... Sigma 3, 0 is the complex conjugate of 0. It's Hermitian because 1 is a real number and minus 1 is a real number.
Did you mention?
Yes.
I might have missed, because I remember in your first lecture you said the traceless property is important.
Yes.
But did we go over why?
Now, here, this is the reason. Yeah. Okay, remember, 1 is the complex conjugate of 1. Right? Minus 1 is the complex conjugate of minus 1. So a Hermitian matrix must have real entries along the main diagonal. Along the main diagonal. Remember, this is what we call the main diagonal, the main diagonal, the main diagonal. And this is what you call the minor diagonal, the minor diagonal, the minor diagonal. So when mathematicians mean transpose, they mean transpose with respect to the main diagonal. Because you could have a transpose with respect to the minor diagonal. Okay? So here you see I is the complex conjugate of minus I. And 0 is the complex conjugate of 0. So these are Hermitian matrices. Now, why do you want to impose the traceless condition? The trace of this matrix is 0. This is traceless, and this 1 minus 1 is 0. So all these three matrices are Hermitian and traceless. Why? Remember when you took a course on matrices? Remember that the determinant of a matrix can be written as the exponential of the trace of the logarithm of that matrix. Remember that? Are you familiar with this formula for the determinant? The determinant of a matrix is given, I can prove it to you if you want to, is the exponential of the trace of the log. Does it ring a bell? To find that the determinant of it can be written as the exponential of the trace of the log.
Because this is a product of the...
Yeah, yes, in a very pedestrian way is that, for example, the determinant of a matrix, okay, which you want to use the letter M for matrix, okay? So in reality, if this is the same thing as the exponential of the log of the determinant. You know, this is an identity, because if I exponentiate something and I take the logarithm, I end up with the same thing. It's like 2 is the same thing as 2 squared, and then I take the square root. So essentially this is identically equal to this. You call this a tautology, okay? Now, if you imagine you have diagonalized a matrix, let's suppose that you have diagonalized a matrix. Okay, so the determinant of your matrix, if it's a diagonal matrix, it's equal to the product of the elements along the diagonal. You know, in a very, you know. So this will be the logarithm of the product of the, you know, of the diagonal elements, 1, lambda 2, lambda sub n, for example. And we know that the logarithm of a product is equal to the sum of the logarithms, right? Yeah. So this is log of lambda sub 1 plus log of lambda and so forth. Okay, so this summation Summation is what you mean by a trace, the trace of the log of your matrix. Okay? So this is why you have this formula over here. Remember, you could have any matrix you want here. If the matrix is not diagonal, it doesn't matter because you can always diagonalize the matrix. Well, if it's non-singular, because then you can bring it in the, if it's singular, then you have to bring it into the Jordan form, which has diagonal and upper diagonal elements. But for the time being, just look at this. So essentially the determinant equals to the exponential of the trace of the log. Now remember that if this is a group element, I'd show you that the group elements are given by the exponential of the generators of your algebra. Remember that the group element G is given by the exponential of your generators with suitable parameters, which you could call the angle parameters if you want. So the logarithm of the exponential is you just kill the logarithm of the exponential is this. Now, because the matrices are traceless, the trace of this is 0, so the exponential of 0 is 1. Okay? So this is why the traceless conditions is so important.
So what does determinant of G equals 1 mean?
Well, this means
G is the generator?
No, G is the group element, and the generators are sigma.
Okay, so determinant of
an SU2 group element. Okay, one.
Why?
Because this is how you define by the special unitary group. The special unitary group is such a group that is unitary and it has an extra condition that the determinant of the matrices are 1.
But that is only for
S.
special unitary group.
Yes, special unitary group.
So does that mean that the traceless property that you mentioned earlier is a requirement only for the special?
Only for the special unitary.
Or for any
No.
groups?
Only for the
Only
special.
for special.
Only for special, yeah. For the special orthogonal or special unitary, okay? Or special symplectic, okay? So
Sorry, is that what makes them special? That's
what's American special,
given
yes.
that degree of freedom by one.
Yes. I'm in South America with these flies and mosquitoes. It's the Zika. The Zika. Yes. Yeah, it's okay. Yeah. Now, let's look at the algebra per se, and the SU2 algebra. Here, when you have those Pauli spin matrices, the composition of two Pauli spin matrices gives you this. It gives you the identity element, the unit matrix, your epsilon tensor, right, and your JK. So the commutator of the Pauli spin matrices is given by this formula over here. Now, what happens if you redefine your generators? You redefine your generators, first of all, by dividing by 2 and multiplying by I. Because remember, these matrix generators were Hermitian. When you multiply by I, you convert them into anti-Hermitian. And when you divide by 2, what happens? You want to divide by 2 because we want to get rid of this 2 over here. You see this 2 over here? The reason you have a 2 here is because these matrices really anti-commute when they are not equal to each other. So when you take the commutator, you end up with an extra factor of 2. So imagine you divide by 4 on the left-hand side. If you divide by 4 here, and if you divide by 4 here, you can rewrite this expression in this form if and only if you redefine the X generators like this. Remember, since, like Raymond was saying, I multiply here by I, but let's suppose we were to multiply by minus I instead of plus I. So in that case, if you were to multiply by minus I, you will get rid of the minus sign here and you will have had a plus sign. Okay, it's just a convention. It's just a convention. But in order to be, yeah, so I guess it's more elegant to have a plus here because it looks more like the Quaternion. Yeah. It's just a matter of convention, you know. But okay, so the bottom line is that by rewriting these generators in this way, you reproduce the algebra of rotations in 3 dimensions. Now let's look at the exponential of this expression. The x, you remember I defined them like this, 1/2 of the Pauli generators. I had an I because remember, this object here is Hermitian. The I makes it anti-Hermitian. And why do you want to have an exponent that is really anti-Hermitian? Okay, why do we want to have an exponent that is an anti-Hermitian? The reason is because I told you that the unitary matrices are such that the inverse are the same as the Hermitian adjoint. So if my matrix is anti-Hermitian, you know, let's suppose I take the complex, the Hermitian adjoint. Okay, I have this. Now, if my matrix is anti-Hermitian, this means that the Hermitian conjugate is minus the matrix. And why do I want to have a minus? Because when I have a minus, I can write this matrix as the inverse like this, right? Okay, so this is the Hermitian adjoint of a unitary matrix. Here I will reproduce the same matrix but with an inverse. So this is why this is called unitary, because the Hermitian of that matrix will give me the inverse of the matrix. And in order to do that, you need to have an object whose Hermitian adjoint will give you a minus sign here. Okay? So this is why it's very convenient to work with anti-Hermitian generators. You know, physicists don't like to do that, you know, because they are very stubborn. And remember, Pauli, the matrices that Pauli wrote are Hermitian. So in order to make them anti-Hermitian, you need to multiply all them by I. Okay? Now let's perform a Taylor expansion of this exponential. Remember, when you square a Pauli spin matrix, you're going to get, you know, when I equals to j, you're going to get a 1 here. And the antisymmetric part will be, you'll kill it, because you know the epsilon symbol, when 2 of its indices are equal, is 0. Okay, so when you square the j, you're going to get 1, and when you don't, and then when they are different, when I and j is different, this is 0, and you will end up with the third term, right? So when you do the algebra, remember these are 2 by 2 matrices. You have to do a Taylor expansion. You're going to have a collection of 2 by 2 matrices. You're going to have a bunch of them. But when you add them all together, when you compile them, and when the dust settle, you end up at the end with these 2 by 2 matrices, given by this expression here. You know, this is like the Euler formula. You know, the Euler, the e to the exponential of I theta is equal to the cosine theta plus I theta. Now, remember what I meant by this hat in an angle? Remember, this hat was the normalized unit vector. Okay, so here I'm using the Einstein summation convention. When the indices are repeated, I have to sum over all the indices, j equals 1, 2, 3. I have by an angle here, I mean the norm of the angle. Remember that the norm of your angle was the square root of theta 1 square plus theta 2 square plus theta 3 square. So this theta here is the norm of your angle. And these theta hat are the components of your unit angle vector. Remember in the first lecture? Anyway. Okay, so now when you go ahead and plug in the expressions for your Pauli spin matrices, you know, when you go back and you plug in these values, you know, then you're going to you end up with this matrix here. You have a 2 by 2 matrices. You end up with a cosine theta here and here because it's the unit matrix. But remember the J3. Remember the J3? The J3 had 1 and minus 1 along the diagonal. So because you had the plus 1 and minus 1 along the diagonal, you end up with this. And then, of course, the J2 and J3 component, J1 and J2 will give you this expression here. Now, if you want to verify whether or not the determinant of this matrix is equal to 1, you can do the algebra and you can check that, in fact, the determinant is, in fact, 1, if you did the algebra correctly. Okay? So, okay. So here I have my definition. By theta, I mean the norm of the angle. By theta hat is the angle normalizes the unit angle. And the prior complex matrix, this matrix, can be written in another form. You can rename the entries of this matrix. Let's rename them. Let's relabel them and give them other names. And we can rename the entries of this matrix by alpha, alpha star, beta, beta star minus. You know, it's just a renaming of the entries of the matrix. Then these are complex numbers, you know, and then the unit determinant condition, you know, when I take the determinant of this matrix, I take this times this. This is what I get. You know, you can verify that, in fact, this is true after you plug in these values of beta and alpha. Okay? Yeah. So therefore, I can verify that the group SU2 manifold, well, the group, in fact, SU2 can be thought, the group itself, the SU2 can be thought as a manifold that is parametrized by the two complex numbers and is diffeomorphic to the 3-sphere. Because if I write alpha in terms of the real and imaginary values, and beta in terms of its real and imaginary values, the determinant becomes this equation, and this is the equation of a 3-sphere of radius unity, and it's embedded in a flat space-time in 4 dimensions. I have 4 coordinates, but because I have this constraint, the norm of these vectors is constrained to 1. What I have is a 3-sphere in 4 dimensions. The reason I have 4 real dimensions is because I have 2 complex degrees of freedom. SU2 is related to 2 complex degrees of freedom. It's related to a 2-dimensional complex space, which is like having 4 real coordinates. Okay? So the unit... Yeah, quaternion, yes. So the unit norm has to do, it's a norm 1 quaternion, okay? So the 4 real coordinates of each point are represented by the coordinates. For example, a 2-sphere embedded in R3 obeys this equation. A 3-sphere embedded in R4 obeys this equation, okay? Yeah. Quaternions, let's go to quaternions and SU2. So in fact, the Pauli spin algebra really is isomorphic to the algebra of unit quaternions. Okay, remember, when you have an algebra, you must never forget the identity element. Because whenever you have an algebra, you have to have an identity element. So the unit matrix is what I call the unit. In boldface, this is the unit element. And then you see a quaternion number can be decomposed in 4 pieces. The first piece is the real part, and you have 3 imaginary units. E1, E2, E3 is what you call the 3 imaginary units. A complex number has only 1 imaginary unit, but a quaternion has 3 imaginary units, E1, E2, E3. And E0 is related to, to the unit matrix. This is the real part of the number, and this is the imaginary part of a quaternion. But the imaginary part has 3 degrees of freedom. Okay? So now when you multiply quaternions, you see a 1-dimensional quaternionic space. The reason I use the letter H for quaternions is because Hamilton is the creator of quaternion. And so we use the letter H instead of Q.
Because Q was already used.
No, because in some books they use, in your book by Gilmore, he uses the letter Q for quaternions. Yes. So the algebra of quaternions is when you multiply 2 unit quaternions together. For example, if you have E1 times E1, the antisymmetric part will be 0. So E1 times E1 is minus 1. Minus 1 because E0 is the identity element. By 1 I mean the identity. 1 I mean this boldface 1. It's not the one, by one I mean an element of your algebra, the unit element. So the square of two imaginary quaternions is equal to -1. You know, it's the analog of the square root of -1 being I. I squared is -1. But here you have 3 of them. Of course, when I is not equal to j, this is 0, and you reproduce the third quaternion. Okay, so it's like a rotations in 3 dimensions, you know, like the composition of Lx with Ly gives you Lz, you know. And then note, so the squares of the imaginary elements are given minus the identity -1. E1 times E2 is E3. E3, E1 times E3 equals minus E2, and so forth. Okay, so this algebra really looks very much like the algebra of the Pauli spin matrices after you multiply by the square root of -1. Let me just go back to it. Okay, so the one-to-one correspondence between quaternions and the Pauli spin matrices is that I assign the identity element to the unit matrix, and the imaginary, remember I have 3 imaginary quaternions. I have E1, E2, E3, and I have 3 Pauli spin matrices. Now by this I mean the square root of -1. Okay? Do not confuse this I, the square root of -1, do not confuse this object with the 3 imaginary units of quaternions. Okay? This is something that causes a lot of confusion with many people. They think that E1 is an I. Sometimes they think that E2 is an I, and they think that E3 is an I. No, you have to be very careful. By I mean the square root of -1, which is a real number. But here I have when I take the squares, I have this. When I square these objects, I get a unit matrix essentially. Okay, so it's very subtle. So just be very careful. Be very careful. Don't confuse this I with any of the imaginary units. Okay, so if I relate the Pauli spin matrices to the unit element, the diagonal matrix, with the unit element of quaternions and the 3 imaginary units, if I relate them in this manner, then what happens is that the quaternionic multiplication table, becomes isomorphic to the Pauli spin matrix multiplication table. There's an I here. I'm sorry?
Historically, it's the reverse because the quaternion existed 100 years before the poly.
Okay.
Poly maybe
didn't know about Hamilton? They didn't know about quaternions, yeah.
Invented something more complex.
Yeah.
So sigma and E are the generators of that?
Sigma 1, sigma 2, sigma 3 are the generators of the SU2 algebra.
Correct.
Okay?
E1, E2, E3 are the generators of the quaternion.
Yes. And this is the map between the two.
And this is also exactly the same as the CL3 algebra.
Yes.
So why do we have 3 different algebras for the same thing?
Yeah, well, that's a good...
Because people are not respectful enough toward Hamilton.
Yeah.
They just wanted to reinvent the thing.
So Hamilton was before Clifford?
Yes. Let me see. Clifford was in the 1850s, but Hamilton was also in the 1800s.
Yeah, I think we looked at it. This was the same time.
1843 as a quaternion.
Quaternions. The octonions were discovered by Cayley and Graves.
Yeah.
Graves and Cayley. Graves first and then Cayley later. But Graves was the first, yeah. Okay.
10 years than the quaternion.
Wow, amazing. Now, when you look at the quaternionic norm, yeah. Now, how do you find the quaternionic norm of a quaternion? What you do is you take a quaternion, remember, this is the first component, and here are the 3 imaginary components of the quaternions. The quaternionic conjugate, in other words, quaternionic complex conjugate, but that really is a misnomer. You should say quaternionic conjugate, because a quaternion is not a complex number. You should say quaternionic conjugate operation. What you do is you reverse the sign of the imaginary units. And despite the fact that the quaternions do not commute, you have to be very careful when you multiply these objects together because they don't commute. Remember, you have to be careful in which order you order the products. But in any case, when you take into account that the quaternions obey this algebra, then when you do the calculation in a piece of paper and you realize that the quaternions obey this algebra, at the end of the calculation, you will end up with this expression here. So this is what you call the norm of a quaternion. The norm square, I'm sorry. The quaternion, I should say the norm square to be more precise. So you get the square of the first plus the square of the second. Yeah. QC. Oh, I'm sorry. My brain. You know that my brain. I'm sorry. But you know what I mean, right? You know what I mean, right? Yeah, you know what I mean. If I don't make mistakes, it'll be. I mean,
it will be boring.
It will be boring, yes. But it's very good for you, because then in this case, I know that you are paying attention, right? Okay. Now the seventh sphere similarly represents the octonions of the unit norm. Okay. Yeah.
Side question.
Yeah.
For the quaternions, all the points which square to -1.
The quaternions to square to -1?
Right, the roots of -1.
Well, yeah. But remember, -1, I mean -1 matrix. -1 matrix. Yeah. Yeah.
Would there be a discrete set of points, or would there be like?
No, because remember, you could have a whole three sphere, a continuum of points, and each point on the three sphere represents a unit quaternion. Yeah, you have a continuum of them.
I'm just worried about the solution to the algebraic equation.
Well, you have an infinity of them, because all these numbers, this quartet of numbers, all of them, if this is equals to 1, all of this quartet of numbers will represent points on the three sphere, and you have a continuum of them.
But not all of them of unit norm will square to be -1.
No, okay. Remember, what squares to -1 are the generators of the quaternion algebra. Okay, remember, the q's are just real numbers. Q0 and Qi are just real numbers. Now, E0 and Ei are the generators of your algebra. Okay, it's like when you write a complex number, you write a complex number is A plus Bi. I really is your generator of your complex algebra, and A and B are just numbers. Okay, don't confuse. Yeah.
If you take any point in the three sphere S3, you name it U, for example, because it's unitary.
Yeah.
It can replace the I of the complex number. You can have a complex algebra with 1 and this U from the S3, and all the formula are the same.
Yeah. Okay. So I guess when you
not only I, J, K, but you can take any U on the sphere.
Yes.
And it will have exactly the same rules as the I from the complex number. And for example, so the rotation is cosinus theta over 2 plus sinus theta over 2 U.
Okay, let's go back to, let's look,
And this is the same formula that you had before.
Here.
This, yes.
Well, here I'm taking the contraction of these generators with this angle. So you mean you want to replace
I, theta hat, J,
by something else, by a linear combination of something else?
A linear combination of I, J, K, the quaternion, but which is on
yes. You can write, remember, you can write this equation. If you want to write this equation in quaternionic form, right? You can. You're right. I mean, you could replace I times. You can replace this by. You're right. By a quaternion entry. Yes. Pure imaginary. Yes. Oh, yes. Yes. Yes.
Then you have the same formula.
Yes. So what Raymond is saying, I'll just wait for them. What Raymond is saying is that you can represent this, what I wrote here. Yes, of course. You can represent this by this. You take E0, okay, cosine the angle, and then it depends on how you choose to rotate, you know. Then you have your quaternion element, I, and then you want the hat, like this, and then the sign of the angle. Yes. You can,
Show that in the next slide.
Yeah.
Because sigma is written as IE.
Yeah.
So that is,
Yeah.
This is my question, I guess.
Yeah.
If you can read that.
Yes. Well, go ahead. Yeah, go ahead and find the solution. No, because the norm is always positive, definite. Is that the norm or just a q square? Is it?
What is the set of quaternions
Ah,
who fill the algebraic
yeah.
relation?
That's it. Oh, okay.
Negative,
Okay. You mean by you take a quaternion, you square it.
yeah.
Okay, but then in that case it gets more complicated because you have to solve. You're going to have you have to solve 4 equations because you have 4 numbers. One of them has to be real, equal to -1, and the other had to be all 0. Yeah. So that's right. So you end up with Okay. So you end up with 4 equations with 4.
why is he writing q squared?
Yeah, you get 4 equations with 4 unknowns. You're going to get 4 equations with 4 unknowns. One equation has to be equal to -1, and the other 3 equations has to be equal to 0. Yeah, I can solve that for you. I mean, I can try to solve it, but you're okay. Here, okay. Let me answer your question. What he's saying, what Dagan is saying is.
The solution is probably all the.
No, it's more complicated because now you're going to have 4 equations with 4 unknowns, and the equations are quadratic. It's not trivial. No. In that case, yeah, if you write a quaternion like this, okay, E0 plus Q2, and then you are squaring this. You're not taking the norm. You're not taking this times its complex conjugate. You're just squaring. Okay. Then of course, if this equals to -1, okay, this -1. Okay, he's writing. Yeah, -1. I can write this -1 like this. -1 plus 0 I1 plus 0 E2, right? Plus 0 E3, right? Okay? So here, when I square this, I'm going to have something which is real, right? And then you have something that multiplies E1, something that multiplies E2, and something that multiplies E3, right? Okay? So then what I have to do is I have to equate this to 0. You end up with one equation. When you equate this to 0, you end up with another equation. And when you equate this to 0, you end up with another equation. And when you equate this to -1, you end up with another equation. So you'll be stuck with 4 equations with 4 unknowns, Q0, Q1, Q2, Q3, that solve this system of 4 quadratic equations, right? It's not trivial. Absolutely.
Why do we want to solve this?
It's a question he asks. He wants to toy. He likes to toy.
To solve a
Yeah.
We know already some solution, I, J, and K.
Either a discrete set of points or
Minus I, minus J, and minus K are
Yeah.
solution.
Yeah, but remember, because remember, when you take the norm, you see, when you take the norm, you have to be, yes, yeah. Anyway, the norm is real. Yeah. Okay. You see, this norm is real by definition, but Dagan is not taking the complex conjugate. So he's having positive and positive here, so it's more complicated, yeah. Okay. Well, I mean, you're very good with computers. I'm sure you can go to Mathematica and just toy with it, yeah.
Probably this is more simple than this.
Maybe you could find a trivial solution. Of course, there's always a trivial solution, but you want to look for you'll have a manifold of solutions. You should have a manifold of solutions. But maybe it's not a sphere. It's a quadratic surface, probably.
So yeah, I suspect it's a surface.
It's a quadratic surface. Yeah.
For complex numbers, you have like a quadratic equation. You have two roots exactly.
Yes.
So that's like a S0 of solutions.
Yeah, so you'll have a quadratic surface, I would imagine. Maybe it has a name. Maybe it has already been discovered and it has a name. Yeah, people who work with, this is a typical problem in algebraic geometry. You know, it's one of those surfaces. Okay, now let's go to this point. Why SU2 is the double cover of SU3? You see, you probably heard that the spin group is the double cover of the rotation group. The reason you have a double cover has to do with this half angle here.
What's double cover?
That 2 to 1.
S.
I'm sorry?
S minus S.
Yeah, but double cover means that you have, when you map, remember when you have a function, y equals phi of x, sometimes you could have 2 solutions to the same equation. You know, like in a quadratic equation, right? You have a solution and its complex conjugate. Here, or 2 real solutions. In this case, notice that when the angle is 360 degrees, when you perform a rotation by 2 pi, because you are dividing by 2, what's going to happen is that you end up with cosine of pi, which is -1, right? Now the sine of pi is 0, so the cosine of pi is -1. So what happens when you perform a rotation of 2 pi, you do not end up at the same point. You end up at the antipodal point, you say that? The antipode, -1.
720.
Yes, you have to go twice, you have to go around 4 pi in order to arrive at the same point.
So
Okay.
if you guys remember, since we were going through the Clifford lecture, that thing written in the parenthesis is a spinner. And we saw that in spinner, S and minus S will give you the same rotated vector,
Yeah,
which is the double cover.
yeah. That's not because you are teaching, yes. So this is why you call the SU2 is the double cover of SO3. And then of course in the mathematical parlance, you can say that the unit quaternions also represent rotations, and you have the kernel is +1 -1. This is what Amrik was saying. So essentially, what we're saying that SU2 is also identical to one of the symmetry group of spinners. So a spin is the double cover of SON. So what happens when you remove the letter S from here? You end up with pin. And if you remove the letter S from O, you end up with O. So people like to play with words. Okay, fine. Remove the S, you end up with pin. Remove it with S, you end up with O. So this is why the pin group is the double cover of the orthogonal group. And if you add an S, you call the spin group is the double cover of SON. This is just nomenclature. Yeah, semantic. Yeah, you are right.
The pin is the non-special.
That's right. Okay. Oh, I'm blocking your way, Park. No. Okay, yeah. Okay, what an SU2 rotation looks like, since Amrik is here. So remember, I'm going to represent a rotation in 3 space in terms of 2 by 2 matrices. Okay, this is very subtle. Remember, usually when you have a 3 space, you think of a vector with 3 components. But here, I'm going to be playing not with 3 by 3 matrices, I'm going to be playing with 2 by 2 matrices. Okay, this is a very subtle point. Okay, but remember, we said that the Pauli had 3 matrices, sigma 1, sigma 2, and sigma 3. The 3 Pauli spin matrices. So intuitively speaking, you can imagine that the 3 Pauli spin matrices are going to represent the x-axis, the y-axis, and the z-axis. Okay, in the Clifford algebra language, this is what you call a vector, polyvector, anyway. But in reality, it's sigma 1, sigma 2, sigma 3. Since Amrik is here, the Pauli spin matrices really is it's a Clifford algebra in 2 dimensions. You see, when you have a Clifford algebra in 2 dimensions, okay, remember you're going to have, okay, when you have 2 times raised to the is 4, you're going to have 4 generators, because 2. Remember the dimension of a Clifford algebra, of a real Clifford algebra, okay, is given by 2 to the n. You know, it's like the number of bits. So when you have a Clifford algebra in 2 dimensions, you're going to have the unit generator, of course, okay, which is a 2 by 2 matrix. You're going to have the generator of your algebra, which is gamma sub 1 and gamma sub 2. Because gamma 1 and gamma 2, these are the generators of your Clifford algebra, and you call them gamma. This is what people use. What happens in 2 dimensions, it happens that the gamma 1 in reality is the Pauli spin matrix 1, and the gamma 2 is the Pauli spin matrix 2. Okay? And as Andrew has been teaching to you, in 2 dimensions you could have the antisymmetric product of 1 and 2, which is like an area. This is your bivector in the 1 and 2 direction. In your 1 and 2 direction, you know, you antisymmetrize. And when you do this algebra, you get sigma 3. Okay? So sigma 3 in reality is just the bivector 1, 2. Which notation do you want me to use? This notation or?
This is what I'm using.
Yeah, okay. Okay, so this is why the Pauli spin algebra in reality is the same thing as a Clifford algebra, a real Clifford algebra in 2 dimensions. Okay? So in reality, this is sigma 1, is gamma 1, gamma 2, and this will be the wedge product. Anyway, so here you have a 2 by 2 matrices. You multiply by the left by a unitary matrix, and here you multiply on the right, because I didn't have space here. Remember, here your combination of, remember x, y, and z are the 3 components of a vector in your 3 space. Sigma 1, sigma 2, and sigma 3 are like your basis vectors, you can think of them. And remember, you sandwich your vector between 2 matrices. This matrix, call it U, and this is the U unitary, the U inverse. Because remember, this object here is the Hermitian conjugate of this guy. Remember, 1 is the Hermitian conjugate of 1. If you have a Hermitian matrix, the Hermitian conjugate of sigma is the same. The Hermitian conjugate of minus I is plus I. So remember, this is like my matrix U, and this is like my inverse. So in reality, this rotation looks, I mean, you could write it as a matrix, you know, as some sort of vector. You could use vector R, and the U minus 1 inverse. Okay, think of it as rotating a vector. So you act on the left by a matrix, you act on the right by another matrix, and then because you have a product of 2 matrices, 2 by 2 matrices, then at the end of the day you're going to have another 2 by 2 matrices. Okay? So you want to find what is the relationship between x prime, y prime, and z prime in terms of x, y, and z. So in other words, this product of matrices will allow us to read the relationship between x prime in terms of x, y, z, y prime after the rotation between x, y, z, and z prime. Okay? So when you go ahead on a piece of paper and you multiply these matrices, you do all the algebra, then what you get, you're going to get, let me just give you the answer. You're going to get, okay, I'm going to give you an example. For simplicity, I choose phi 1, phi 2 equal to 0 to make our life easier. Phi 3 to theta. My unit angle is given by this. And then when you do the algebra, remember my SU2 matrix is this. Don't forget the trigonometric identities. Remember, cosine theta is given in terms of the half angle formula. Remember in trigonometry how to express the cosine theta in terms of the half angle. And remember, the sine is given by this formula. And only because you have these trigonometric identities, let me just go back here. Remember, here I have half of my angle, half of my angle, half of my angle, half of my angle. So, but when I multiply those matrices together, I'm going to reproduce my whole angle. Instead of having half of my angle, I'm going to have my whole of the angle. Why? Because you are going to have these relationships between the half angle and the angle. So at the end of the day, essentially when you multiply this matrix by this matrix by this matrix, you end up with this. You end up with a 2 by 2 matrix. You end up with Z here minus Z. Remember, the reason you have this minus Z here is because the third component of the Pauli spin matrix had a 1 and minus 1 along the diagonals. So when you do the algebra, you're going to have a plus and a minus. And then the sigma 1 and sigma 2 are off the diagonal, so you're going to have, this is what you get. So here I have the entries of a 2 by 2 matrix. Here I have a 2 by 2 matrix, so I'm going to equate this. I'm going to equate this entry with this entry. I'm going to equate this entry over here with this entry over here with this entry, and this entry with this entry. So when I match the entries of both matrices on the left and right hand side, I arrive to this conclusion. I arrive that Z equals to Z prime. Why? It's because I have performed a rotation along the Z-axis, so it doesn't affect the Z component of your vector. And whereas the X coordinates and the Y coordinate get entangled, so I end up with a rotation. So the net effect is the same as multiplying the SO3 3 by 3 matrices, you know, and you see a 1 here. This 1 is what lives invariant the Z component. Okay, so let me just go back to it because this is actually very important. You know, by an SU2 rotation I have of this 2 by 2 matrix involving the X, Y, Z coordinates, I perform an SU2 rotation. And after I do the algebra, I end up with this. And this is the same thing as if I had rotated the components of a vector in 3 dimensions. If I use these 3 by 3 rotation matrices, if I multiply by a column matrix to get a 3 by 3 another column matrix. So you get the same answer if you use SU2 rotors to be, or SU3 matrices. Okay, so they're equivalent. You know, the only subtle thing is that you have to remember is that don't confuse them. That in reality, let's go back. That here you are dealing with 2 by 2 matrices. Here you are dealing with 2 by 2 matrices. And here we are dealing with vectors in 3 dimensions. Okay? So do not confuse the basis vector. You have the basis.
The generators are 2 by 2,
Yeah.
but the space is 3 dimensional.
Yes, yes.
So,
Yeah.
okay, this is more of a philosophical
Yeah.
question
Yeah.
that I have.
Yeah.
So you have SU2, so SU2, Quaternions and
Yeah.
Clifford algebra.
Yeah.
The generators produce the same algebra.
Yes.
However, the form of the generators are very different. So one is a matrix, the other is a vector. In case of Clifford algebra, vectors and bivectors.
Yeah, but remember, the Clifford algebra admits a matrix representation. The Clifford generators admit a matrix representation, which are the Dirac matrices, for example. In 4
When you say admit, do you mean isomorphic or?
No, the algebra can be represented in many different ways. And one representation is a matrix representation.
Yes, so that is my question.
Yeah.
So why,
Yeah.
so what's the art here of choosing the representation? Like
That you have to be clever. You have to be clever to realize what representation to choose. For example, when you work with the Clifford algebra in 4 dimensions, you could choose the Majorana representation, where the entries of all your gamma matrices are all real, all imaginary, or you could choose the Weil representation, which is called the Callan representation, which is you have your 4 by 4 matrix can be written in block form of 2 by 2 matrices, You know, there are many, infinite number of ways you can do it, but you have to be clever. You
There is an exercise in the book about this.
Yeah. An exercise, yeah. So now, in 2 dimensions, remember the Clifford in 2 dimensions, the Clifford algebra generators in 2 dimensions can be represented by two matrices, which happen to be the Pauli spin matrices. Okay? Yeah. When you go to higher dimension, it gets more complicated because the size of the Clifford matrices keep increasing and increasing and increasing in size. For example, when you go to 8 dimension, the Clifford algebra is 2 to the 8 is 256 dimensional. When you take the square root of 256, you get 16. So you are stuck with 16 by 16 matrices. You know, so you have 256 matrices. Each one of those matrices is 16 by 16 in size. And they represent the Clifford 8 algebra.
So one would imagine that
Yeah.
using a matrix representation is computationally
Not
more
efficient.
more efficient.
Not.
Because I have 16 by 16 is much easier to tackle than 256 different bases.
Yeah, but if you are but remember, when you write the Clifford algebra in abstract form, you never write matrix indices. You only use the vector generators or bivectors. You never worry about the matrix representation. You use this all symbolically and algebraically. You never introduce, for example.
That's my question, because it seems contrary to my intuition, because I would rather prefer using matrices which
Yes.
are compact and less dimensional.
Yeah, but if I give you a 16 by 16 matrix with a bunch of entries, and I ask you to multiply them, but remember, in those days, those guys didn't have computers. So remember, a Clifford algebra, for example, it's given by the anti-commutator, you know. So this is plus ji. Okay, so this in reality is 2, the metric of your space, you know, times the unit matrix. You see, nobody writes the unit matrix. In reality, you could represent your gammas. Your gammas can be represented in terms of matrices, you know, alpha, beta, you know. And a column matrix that is has zeros everywhere, for example, except the first column, or a row matrix that has zeros everywhere except the first row, is what you call spinors. Spinors, from the Clifford point of view, are left-right ideal elements of the algebra. Okay, so essentially a spinor is like a column, you know. Imagine you take a matrix, you throw all the columns and you keep one column, that looks like a spinor. Okay, so in general, of course, you could write explicitly the matrix indices, but nobody does this, you know.
Is it because of historical reasons?
Yes, yeah.
Because this seems to be a smarter choice in the contemporary era.
Yeah, that's probably true. But remember, don't forget, you should include a 1 here because it's your element of your algebra. Now, if you want to include entries to your matrices, then you always have to remember, then this is the unit matrix, and these are the entries of your unit matrix. Ij label the generators, remember, these indices label the generators, and alpha and beta label the entries of your matrix, okay? But it's somebody who is very good in Clifford algebras will not multiply matrices together. He will do this algebra in his head, you know, automatically, you know. In one of the lectures I'll be presenting, I'll be writing the commutation relations of all the Clifford generators, the bivectors, the trivectors, the four vectors, and you will see how powerful it is when you know the algebra without knowing the matrix representation, because there's an infinite number of them. You can remember this algebra is invariant under how do you call it, similarity transformation? You compare on an automorphism. You know, you can replace the gamma generators by other gamma generators, and still they may satisfy the same algebra. It's like having a matrix and you find a different representation. But the algebra should remain the same. Yeah. Okay, can I proceed? Can I proceed? Yeah. Okay, the Lorentz Group. Okay, since Amrik is here, he's going to teach you about the Lorentz Group. I'm just going to briefly say how you can get the Lorentz Group transformation as a complexification of SU2. Remember I told you in the first lecture that the cosine of an imaginary angle was related to the hyperbolic cosine? Remember I mentioned this? And then the sine of an imaginary angle is related to the hyperbolic sine. So a Lorentz, let's suppose that you perform a Lorentz boost along the x-axis. Remember that I told you earlier that a boost transformation along the one direction, x-axis corresponds to the first axis, is like a rotation involving the temporal direction. So 0, 1 is the bivector involving the temporal direction with the spatial direction, you know. And because of this relationship between the hyperbolic and sine, hyperbolic cosine, and hyperbolic sine in terms of the cosine of the imaginary angle, you can perform a rotation like this. And here I have gamma 0, gamma 1, gamma 2, and gamma 3. In reality here I have a Clifford algebra in 4 dimensions. Remember, Clifford algebra in 4 dimensions, there is 2 raised to the power of 4 is 16, right? 2 to the 4 is 16, so you need 4 by 4 matrices, because 4 times 4 is 16. So one representation of the Clifford algebra in 4 dimension, okay, is by having, let me see if I remember. You take phi 1, the first generation, remember, and then of course don't forget there is the temporal component of your algebra. One representation is having, remember this is a 4 by 4 matrix. Okay, so what I do is I break it in blocks of 2 by 2. Okay, so I put a 0 here. This is a 2 by 2 0 matrix. Here I put another 0, a 2 by 2 matrix. And here you put the Pauli spin matrix, which is 2 by 2. Here you put the Pauli spin matrix, which is 2 by 2. Okay? You do the same thing with the other generators. This is a representation of your algebra, right? I mean, you'll be talking about this. This is, you're going to have zeros here, and you are going to have sigma 2 here. The same thing with the gamma 3. Okay? Yeah. Okay, and then with the gamma 0, if I remember correctly, if the gamma 0, remember, I think you have to have, I think you want to have a traceless matrix, right?
Yes, with sigma.
You may have the unit matrix here and then the -1 here, if I'm correct. You know, because remember, you want the matrices to be traceless. Okay? I think you have this, something like that. And then, of course, the unit matrix, of course, don't forget, which is 1, you know, 1. And remember, these are 2 by 2 matrices, remember, because overall I have a 4 by 4 matrices, okay? So here I have written down the 4 by 4 Clifford algebra matrix in terms of blocks of 2 by 2 matrices in terms of the Pauli spin algebra. This is the representation. There's another representation. There are many different ways of doing this. But okay, so what happens is when you do the same thing with the t's and the x and the y's and the z's, and you do the, remember, this now will be a 4 by 4 matrix instead of a 2 by 2.
CL4?
Yes, it's
Yes, yeah. And here I will have now a 4 by 4 matrix, because here, remember, here now I have 4 by 4 matrix. And then you do the algebra. Then what do? At the end of the day, you get this. This is what you get. You get the Lorentz transformation of your coordinates. Remember, the y coordinates and the z coordinates remain invariant because I'm performing a boost along the x-axis, along the first axis. So the y and z coordinates will not be affected. The only coordinates that will be affected will be the temporal coordinate and the x coordinate. And of course, why is the temporal coordinate affected? Because Lorentz boost is like a rotation with an imaginary angle along the 0, 1 direction. Okay?
Is it the helical around the time?
Yeah, I guess if you want, well, remember, these are hyperbolic angles. Remember, I'm working with hyperbolic, okay? Remember, these objects are not periodic, okay? Okay, yeah. The camera is on, right, David?
Yes.
Yeah, okay. So remember, just as a reminder, remember that the Lorentz boost parameter can take values from -infinity, +infinity. Remember when you took relativity, the velocity can be positive or negative. You could move along the positive direction or along the negative direction. Remember that we can never attain the speed of light. We only attain this when we attain the speed of light. What happens? The hyperbolic tangent becomes 1, and so therefore the boost parameter becomes infinite. You see, when the boost parameter is infinite, the hyperbolic tangent becomes 1. And so the velocity is plus c. When the boost parameter is negative infinity, the hyperbolic tangent is -1, so the velocity is minus c. So you can move in the positive direction or in the negative direction.
This is a way of rewriting the Lorentz transformation in terms of the algebra?
Yes.
Is that the
Yes.
point here?
Yes. And to interpret the boost parameters in terms of an imaginary angle. Okay? And to relate the trigonometric functions with the hyperbolic functions.
Yes.
Yeah.
So as I said, when you go from the Euclidean space to the Minkowski space, which is an hyperbolic space, you just have to replace the trigonometry, Euclidean trigonometry, by hyperbolic trigonometry, and it's very
Yeah, it's like replacing t by it. You know, this is the what in quantum field theory we call the weak rotation. Yeah, t replaced it. Minkowski did that. Minkowski realized that x squared plus y squared plus z squared plus t squared, if you replace t by the square root of -1 times t, the t squared becomes minus t squared. It's what you call an analytic continuation. Well, a weak rotation. This is the Minkowski trick, to go from Euclidean space to Minkowski space. You know. So here you do the same thing with the angles. The imaginary angles become hyperbolic. The trigonometric functions become hyperbolic. You have a spherical trigonometry. Here you have hyperbolic trigonometry, which is something that some people in school learn, in some good schools. Yeah.
Does the name for the hyperbolic trigonometry comes from this, or was it?
I don't know. I know that in some good schools, like in France, some people used to take spherical trigonometry and hyperbolic trigonometry. Sure, but only in some good school. Yeah. But remember, in this book, I was telling Raymond, in your book by Gilmore, you have, in many chapters, you had very nice drawings of hyperbolic, of hyperboloids. I will point them out to you. It has very nice pictures of spheres, hyperboloids, and the difference between projective coordinates and homogeneous coordinates. We'll go into that. So here, okay, so now this is the hyperbolic tangent. The hyperbolic cosine has this expression. Remember the Lorentz contraction factor? Or remember in relativity? Where if the velocity is equal to the speed of light, the Lorentz contraction becomes infinite. Remember? And the rulers will contract to 0 size. And then in hyperbolic geometry, you have this relationship. You see, in ordinary spherical trigonometry or circular trigonometry, you have the square of the cosine plus the square of the sine added to 1. In hyperbolic geometry, is different. You have here a minus sign here. So you see, these relationships in terms of hyperbolic cosine and hyperbolic sine can be rewritten in this form in terms of the physical parameters, which is the velocity. So when the cosine and the sine and the tangent are related in terms of the velocity, by these relations, you can show that this equation here, okay, becomes the same as this. Okay? So you recover the Lorentz transformations by performing a Lorentz boost, which looks like the complexification of the SU2. Because remember, the SU2 are ordinary rotations with an ordinary angle. Here you are playing with an imaginary angle.
So,
yeah.
The expression there is a rotation, though, right?
Well, for me, it's what you call a rotor, using this bivector.
Yeah.
It's a rotation involving the 0-1 direction.
0-1 direction.
Yes. Rotation, quote unquote, that rotation, quote unquote, is really a Lorentz boost, because in reality the angle is not an ordinary angle, it has been complexified. Okay, so you're playing with from cosine, you're playing with hyperbolic function.
So in terms of the physics, how do I make sense of this? So you performed a rotation.
Yes.
I want to stick with the rotation.
Yes.
You performed a rotation on a vector in Minkowski space, which is your CT gamma naught bar.
Yes.
Right?
Yes.
And you got the Lorentz transformation.
Yes.
So physically, how do I relate that how a rotation of
Well, from the Clifford algebra point of view, is straightforward. From the Clifford algebra point of view, this is a Clifford vector,
yes,
okay, and this is a Clifford rotor.
correct.
You know, so that's from the Clifford perspective, is just a rotor transformation of a vector, of a four vector. Of a four vector. Means a vector in 4 dimensions involving the Clifford call it Clifford rotations, call it a Clifford transformation, a Clifford rotor.
So can this be taken as a general principle to generate any transformations? Like
Yes. Well, I mean, you have to make sure that the
so in a sense, a rotation is going to give me everything.
Yes, you see, the extended relativity theory that I developed many years ago. I have an extension of the relativity theory involving Clifford spaces. So I play with these ideas.
So do you always do a rotor or rotation operation?
Rotor, quote unquote, yes. But instead of having bivectors, I have trivectors and higher grade vectors, yes.
So the generators of your rotor can be different.
Yes. So I'm really working, instead of with a 4-dimensional space, I'm working with a 2 to the 4th, with a 16-dimensional space. So I'm having like an extended relativity theory in 16 dimensions.
What is the corresponding transformation that you get?
It's much more complicated because now you're going to have, remember, this object here, in order to be rigorous, in general, for every generator, you have to associate a parameter. Okay? Here I'm performing an ordinary rotation along the 0-1 plane. So in reality, I have a rotation along the 0-1 plane. I only need one parameter. Okay? But when you have rotations along all the planes, then you need to tell me more. You need to give me more parameters. Okay? Because remember, when I talk about the general rotation, I gave you the 3 angles. You know, and they are coupled with the first generator. I gave you another angle coupled to your second generator. I gave you another angle coupled with the other generator. In Clifford space, you're going to have, if you have this bivector, in reality you have this parameter 0-1, because here I have a 0-1. Then you could have, for example, 0-2 coupled with 0-2 here. And then you could have trivectors. You may have 1, 2, 3 with 1, 2, 3. So you're going to have generalized rotations in your Clifford space. Your Clifford space associated with your ordinary Minkowski space. So if you're working in 4 dimensions, the Clifford algebra is 16-dimensional. So you need to have 16 parameters associated to each one of the generators. Okay? Of course, you only start with your basis vectors. Remember, you only start with your basis vector, right? But then, of course, when you take the wedge product, you generate a bivector, right? When you take the triple product, the triple wedge product, you generate a trivector, you know, and so forth. So, in general, you could have 2 to the 4, in that case, 2 to the 6.
In any case, all your parameters are rotation angles.
Well, you could call them rotation from the Clifford
space.
Yes, from the Clifford space. Yes, you can view them as rotation angles. Yes. But remember,
it boils down to rotations in
Yeah.
different space.
Yes, but now you have to be very careful because the Clifford algebra is very sensitive to the signature of your space-time. Remember, Clifford algebra. Remember when I wrote the algebra that the anti-commutators are given. Don't forget that when you have a Clifford algebra, an orthogonal Clifford algebra, you need to specify the metric of your space. Okay? And so the metric will tell you which signature you'll have. So a Clifford algebra in 4 dimensions is not the same as a Clifford algebra in 3,1 or 2,2, meaning 2 spatial direction, 2 temporal direction, or meaning 3 spatial direction and 1. So the Clifford algebras are very sensitive to the signature of your space. And that signature of your space is codified in what you put here on your right-hand side.
Is that
The metric, this is the metric.
Is that a commutator?
Anti-commutator. Yeah.
Anti-commutator.
It's the bracket.
Powerless.
The brackets, yeah. He's going to the restroom? Yeah. We could talk a little bit until he comes back, yeah.
Yes, Clifford, so you can get the Lorentz Group in the Clifford algebra from Clifford.
Oh, yes.
But my question is not
Of course you can. Amrik will be should be talking about that in his future lectures. Yes, remember when I gave you the commutators of your Lorentz group? Remember that I wrote them like this. Let's write it like this. Okay. Remember that I gave you the answer. I told you that this was IL MJK plus ta 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 ta. Remember the Lorentz algebra? I wrote it like this. So for the Clifford algebra, it's very simple. You can find a realization of the Lorentz group by replacing your Lorentz generator by bivectors. Okay, this is a bivector, and this is a bivector. So the commutator of 2 bivectors is isomorphic to the Lorentz algebra. So the Lorentz algebra, or the rotation group, is isomorphic to the commutator of 2 Clifford bivectors.
So why did you go from, in the first 2 lectures we saw that the structure constant, which is G in your case here.
Well, the structure constant is more complicated than G. I will, when I talk to you, if you want, I will write the structure constant. It's related to G, of course, but it's a little bit more complicated than G. Is of course it has G in it, of course.
I mean, some functional.
Some functional, because you have to take generalized Kronecker delta operators. I'll show you what the structure constants are.
My other question is, why did you go from the commutator relations to the anti-commutator?
Yeah, because the Clifford algebra, in reality, in Clifford algebra they are very good because you have both. You have anti-commutators and commutators.
Is there a reason why you chose the anti-commutator?
Because this is how Clifford defined his algebra. Essentially, a Clifford algebra is essentially taking the square root of 1 or minus 1. In a very pedestrian way, Clifford algebra is nothing but taking the square root of the unit operator or the negative unit operator. That's all it is.
So the
yeah.
Clifford of 4 is 16 dimension.
Clifford 4, yes.
And,
Yeah.
but SL2C is just 6 dimension.
Yes.
So the 10 other dimension.
Well, those involve this. They'll involve trivectors. They involve the other more complicated. You will
correspond to some
yes.
geometry.
You will have to add. You will have to add more terms in here, more terms in here, and more terms in here. Okay.
Yeah, geometrically, which transform?
They are like in Clifford space. In Clifford space, Clifford rotation is like having taking a vector and rotating a vector, or you can rotate a plane, or you can rotate a volume. So imagine you have a parallelepiped. So under Clifford rotation, when you have a trivector, you will have a parallelepiped transformation. So a brick can be rotated into a brick, or a brick can be rotated into a table. So the dimensions change. You can actually change the dimensions of your objects. So the extended relativity in Clifford spaces, a line can be transformed to an area can be transformed to a volume. So you can have transdimensional transformation. This is the standard relativity in C space that I've worked for many, many years. So the dimensions change. So an object, a bottle can be converted into a line, or a line can be converted into a cube. Yeah. Anyway.
And
Okay.
does it predict new physics?
Yes. And the Planck scale is in there, of course. Yes. Yeah, maybe the next time when I come back to see you, I can give a lecture on what the extended relativity theory in Clifford spaces is all about.
Are you not going to talk about it this time?
No, because I have to talk about Lie algebras. We won't have time, unfortunately. Yeah. Okay. So now let's go to. We were working with the SU2. Let's work with the special unitary group in higher dimensions. So the special unitary group of degree n. Some people call it degree n. Denoted by this is the Lie group of n by n unitary matrices with determinant equals to 1. It's a real value determinant, not complex as for generally unitary matrices. The group operation is just simply that of matrix multiplication. And UN is the group that preserves the standard inner product in this n-dimensional complex space. Okay, what are the applications in physics? We know that the SU2 is the gauge group of the electroweak interaction. We know that the SU3 is the gauge group in quantum chromodynamics. We know that U1, in that case, there's no difference between the special and the unitary, because you only have one. It's the gauge group of Maxwell's electromagnetism.
This is the direct sum is the SU5.
SU5 is one of the grand unification groups, the Georgi-Glasgow unification group.
So is it SU3 cross SU2?
No, SU5 contains SU3 cross SU2 cross SU1. SU5 is one of the unification groups. You'll see in the next lecture that there's thousands and thousands and thousands of unification groups. Yes. Okay, now let's look at the fundamental representation of Myalgia. Remember, when I use lowercase, this in German is called Fraktur. The font Fraktur. I use this notation for Lie algebras, whereas I use capital letters, Roman letters for groups. Okay, in that case, remember, SUN has n squared minus 1 generators. Because now n, remember, I told you to look up pages 38 to 42 in your book. They give you the 52. Yeah, the dimensions of your Lie groups. Okay, so in that case, this algebra or this group has these generators. Okay, I'm going to use traceless matrices, because I want the determinant to be 1. Hermitian matrices, if you want to use Hermitians. And where now the commutators and the anti-commutators are given by this relationship. Remember, when you take the commutator here, because remember, if you use Hermitian matrices, you have an I here. So the commutator of 2 generators is going to give you a linear combination of the other generators. These are the structure constants. And remember, I'm using the Einstein summation rule. Well, in that case, no, because I already wrote the epsilon symbol. I'm summing between c equals to 1 to the dimension of my algebra, which is n squared minus 1. Okay, so remember, I'm summing over c equals 1, 2, 3, blah, blah, blah. So the commutator of any 2 elements is given by a linear combination of my algebra generators. Of course, we're going to see what these structure constants are. Now, the anti-commutator, remember, the anti-commutator, you write it as a bracket. It's given by, instead of taking the minus sign here, you take the plus sign. So the they become like this. This is the relationship. And D are called the D functions. The D functions, they're associated with the SUN. Don't worry too much about what these D functions are, because in reality, the algebra really is a Lie algebra, and I only need to focus on the commutator, which is involving the structure constant. Don't worry.
D related to it?
D really is related to the product. In reality, the product of the matrices is the key. The product. This is the product of my matrices. Is given, and then of course you have this constant here, which is made out of 2 pieces. So in reality, what is important is this whole constant here, which can be broken up into 2 pieces. You know, one piece is related to the structure constant of my algebra, and the other piece is to the D function. Don't worry too much about the D function. Remember, if you look up in Wikipedia, you'll see this. And then, of course, you impose a normalization in such a way that when you play with the D coefficients, you have this formula. But don't worry about the D, or don't worry at the moment about the anti-commutator. Just focus on the commutation relations. Now, let's give you another example. What are the generators of the SU3 Lie algebra? So Gilman, with Gilman and Yuval Ne'eman were the ones who proposed the theory of quarks to explain the strong interaction. It's funny that Yuval did not get the Nobel Prize. Gilman got the Nobel Prize, but Yuval did not get the Nobel Prize. For some reason, I forgot. He told me, he hinted at something. I think it had to do with his political views, because Yuval was very right-wing. And you know, the people in Stockholm are more left-wing than right-wing. So I think one of the reasons was political. And I'm being filmed anyway. Yeah.
Which name?
Yuval Ne'eman. He said, yeah, very bright guy.
N-E-E-M-A-N?
N-E-E.
N-E-E-M-A-N?
Yes. And then, of course, if you're Israeli, you have an apostrophe. N-E apostrophe with a apostrophe E anyway. He was a member of the Knesset, of the Jewish parliament. You know, so he was both a politician and a scientist. So he did, and a soldier. He's one of the guys who fought during 1948 Arab War.
He was the head of Army intelligence.
Yes. He was also the Minister of Science, and he also, of course, was one of the people who developed the atomic bomb for Israel. And he went to do his PhD in London at Imperial College when Abdus Salam was in Imperial College. And Moshe Dayan was the one who wrote a letter of introduction to Salam. He said, we have a very smart guy, we would like you to take him as a student. And about 2 years later, he came up with the idea of Quaternion. No, he was very bright. No doubt about that. So people know him in Israel, right?
Yeah, I know.
There is a street in Tel Aviv after his name, you know. The sad thing is that he fell down he bumped his head and he died from complications of the fall. He used to spend a few months in Austin and a few months in Israel and a few months in Germany. So that's what he did most of. No, he had a good life, no doubt about it. Okay, so the Gilman matrices are now, remember, SU3, I'm going to have now 3 square minus 1 is 8. I'm going to have 8 Hermitian traceless Gilman matrices. And okay, so let me give you 4 of them, and then in the next slide.
So is it true that the first 3, if you look at the 2 by 2 matrices,
Yeah.
the poly matrices?
Yeah, imagine here I draw a block here.
Yeah.
So it's like having the 2 by 2 Pauli spin matrices, and I'm going to embed them into 3 by 3 matrices. This is what I do. At least the first 3 ones. So I have embedded the first, second, and third Pauli spin matrix into a 3 by 3 matrix. Yes, the first. Yeah, but I choose. Yeah, but remember now, but there are more matrices. So then look at the 4 matrix. I choose a 1 over here and a 1 in the extreme corner. Because remember, these matrices are Hermitian. So if this is my main diagonal, they have to be symmetric in this case with respect to 1 and 1. Okay, so let's go to the next one. The next ones, look, remember, if they are Hermitian, so I is the complex conjugate of minus I. Remember, if I look at the main diagonal, I is the complex conjugate of minus I. Why? Because I chose my matrix to be Hermitian. Okay? Here, look at this matrix here. Okay, it's symmetric because 1 is the complex conjugate of 1. Look at this matrix here. I is the complex conjugate of I. And finally, I have another matrix, lambda sub 8. Remember, it's traceless. 1, 1 minus 2. It's traceless. Now, why do I choose the square root of 3? It's because all the generators have to be normalized to a convention. No. You have to take the matrices, all these matrices, when you square them, and you take the trace, you're going to get 2. Okay, all these matrices that I wrote, when you square them, remember you're going to have zeros, and here you're going to have 2 when you take the trace of the square. So when you have this matrix, when you square it, you're going to have 1 plus 1 is 2, plus 2 is 4, divided by the square root of 3, which is 3. 6 divided by 3 is 2. So these matrices are normalized in such a way that the trace of the square of each matrix is 2. It's just, and later when we look at the Dinkin diagrams of SU3, and when we study the Cartan matrix, remember, you'll see that the Cartan matrix has 2 along the diagonal, and this 2 is related to this. Okay? Yeah. Similarly, we can obtain. Okay, since America is reading, yeah. Similarly, you can rotate the generator of SU5. Of course, SU5 has 5 square minus 1 is 24, right? So you're going to have 24 matrices. Each of these matrices is going to be 5 by 5. So you're going to have, it gets more complicated, right? But the bottom line is that your matrices are all Hermitian and all traceless. And you use this to build an SU5 grand unified model that unifies the electroweak with the strong interaction. It's called the Georgi-Glashow model. The problem is that because nobody has observed the proton decay, people don't believe in it. But anyway, it's one of the many grand unification models. Yeah. Okay, let's go to, if you look at the Gilman matrices, if you rescale them by 2, by 1/2, you have this algebra. And the non-vanishing structure constants, if you go ahead and take the matrices I just wrote down, if you write down the commutation relationship, you'll see that the non-vanishing structure constant of the SU3 algebra in this basis are given by this. The 1, 2, 3 gives you 1, the 4, 5, 8 gives you this, and all of these guys gives you 1/2. Remember, these matrices, if I remember, they are all antisymmetric. These entries are all antisymmetric. When you reverse any of the indices, the antisymmetric, right? So you choose these generators because it's going to simplify the commutation relations. And the structure constants, the only non-vanishing structure constants are given by this set. And while all the other structure constants, which are not related to any of these by permutation, are 0. Okay? So if you go to Wikipedia, for example, and you look at Gilman Matrices, you'll be able to find this. Okay? I borrow these results from Wikipedia, you know, because I could have gone to a Scholarpedia, but you know, I just chose the simplest thing. Okay? Okay, remember, the structure constants for Lie algebra are always defined with respect a given basis. You know, if you change your basis, you're going to change the structure constants, right? Because let's suppose that I choose my basis in terms of the x size. So if I have this algebra, remember the structure constants are antisymmetric with respect to these two indices. If you change basis, if you perform a change of basis, the structure constants will change. Now the new structure constants are given in terms of the old ones by this transformation matrix. Remember, I have 3 indices here, so I'm going to have 3 matrices. Okay, 2 of them are covariant indices. 1 of them is contravariant. So when you perform a coordinate transformation, you are going to have these 2 matrices that contract the lower index, and the inverse of the matrix will contract the upper index. Anyway, so did I do it right? Yes, the K. Okay, so remember, the structure constants have the transformation properties of a 3rd order tensor, and it's covariant of 2nd rank and contravariant of 1st rank. Yeah. Okay, and let's remember that earlier in the lecture number 2, I talked about the adjoint representation. Remember?
Labeling the matrices.
Yes, labeling the matrices. So you choose the first index. The first index is I, is associated with your matrix label, and your 2nd and 3rd index are related to the rows and entries of your matrix. Okay, and you have, how many matrices do you have? You have as many as the dimension of your Lie algebra. And of course, each matrix is n by n. Okay, so this is called the adjoint representation or the regular representation, you know. Okay, so how do you define the Cartan-Killing metric associated with your Lie algebra, which is a vector space? The Cartan-Killing metric is defined by this. Remember, I'm taking the scalar product of 2 vectors, well, with the components of the vectors. So remember, the Killing metric is symmetric under ij. You can show this. So what you do is you contract this index S with this S, and you contract this R index with this R index, and at the end of the day you'll end up with 2 free indices, and in this way you define the Cartan-Killing metric associated with the structure constants, which tell you something about your Lie algebra. So you give me a Lie algebra by giving me the structure constants. Of course, in that basis that you choose, I can define a metric. Of course, if you change your basis, the Cartan-Killing metric should change, but it should remain invariant, because the Cartan-Killing metric is like a fingerprint of your algebra. So if you change your basis, it should not matter if you change the basis you choose, because the algebra is encoded somehow in the Cartan-Killing metric. I have to check, but I think I think it has to do with automorphisms. Okay, I'm sorry. You have a Lie algebra. If you perform an automorphisms, they will not change the Cartan-Killing metric, because by definition, an automorphism of a Lie algebra should not change the Cartan-Killing metric. Like in the octonions, remember? The G2 algebra is the automorphisms of the octonions. Must preserve some symmetry. So in this case, when you perform an automorphism of your Lie algebra, the Cartan-Killing metric should remain invariant, because this is what an automorphism means. It's like in isometry, if you want to use your words. Yeah.
Oh, asymmetry.
Yeah.
So this is for SUN, right?
No, this is in general for any Lie algebra.
Okay, so so including SUN.
Yes, yes.
If n is equal to 4, will my Cartan killing metric collapse to the Minkowski metric?
No, well, if n equals to 4, are you talking about
I'm talking about SU4.
SU4? Let's talk about the Lorentz group. The Lorentz group, remember, the adjoint representation, okay, how many generators does the Lorentz group has? It has 6, right?
Yes,
Okay, so you will need to have 6 matrices, and each matrix must be 6 by 6.
okay.
Okay? Remember, because the indices label the number of generators of your algebra in the adjoint representation. Okay? Remember, you are right, you can represent rotations in terms of 4 by 4 matrices, but here you're using the adjoint representation, which is not the same as the fundamental representation. You have to be very careful, very careful. In this case, I'm going to have a 6 by 6 matrix. Okay, be very careful, okay? Not to confuse the fundamental representation with the adjoint representation, okay? Now, the E8 is very special because the E8 algebra is very interesting. It happens that the dimension of the fundamental representation coincides with the dimension of the adjoint representation for E8.
And that's the only one?
I think it's the only, yeah, well, there are others, but E8 is, there are other cases, of course, the other cases. Let me give you an example. The rotation group in 3 dimensions. The rotation group has 3 generators, right? So the adjoint representation will be given by 3 by 3 matrices. Okay, so in that case, the adjoint representation coincides with the fundamental representation for SO3. Okay, so the other groups, not only E8, you know, the other groups like SO3, but E8 is interesting because it's an exceptional Lie algebra and the adjoint representation happens to coincide with the fundamental. You know, but the other Lie algebras is not the only one. Yeah. Okay, now what happens when the determinant of the Cartan-Killing metric is 0? In that case, you have a singular metric. So when the determinant of the Cartan-Killing metric is singular, meaning it's 0, you have what you call a non-semi-simple algebra, like U1. If the determinant is not 0, you have a non-singular metric associated to a semi-simple Lie algebra. Okay, so what I'm going to do is I'm going to stop for now. Is that okay? We started around this time, or was it 5:15 when we started?
It was 3:20.
Okay, shall we have 5 more minutes? Or shall we rest? Because yesterday, my God, my throat was... Because then I had to speak to Ramon for 2 more hours. And I had a sore... I really had a sore throat. I really had a sore throat.
So we'll give you a break. Discount.
Yes, yes. Okay, so let me just tell you what will happen tomorrow. Tomorrow, let's see. We'll talk a little bit about simple, semi-simple, non-semi-simple algebra, which is very confusing, but I'll just try to be as intuitive as possible. The rational Lorentz operators for SU2, and then a little bit of tensor products, and then voila, that will be the end. And then I will go to lecture 3 and so forth. Okay? So I hope this was useful. Is it getting better, David, every day? You think I should go to Hollywood and try to be a movie star?